On the next example in 8.7, number 9, they're giving you the graph of these rational functions. And we've established already in this class that none of these have holes. So we're not going to see any matching factors. Okay? Nothing's going to cancel in any of these because there aren't any holes. All right? Are there asymptotes? Yes. So that means we're going to have something in the bottom that doesn't match the top. Are there any x-intercepts? Yes. So that means we're going to have something in the top that doesn't match the bottom. You can distinguish those three things. Holes have a match. Asymptotes, vertical asymptotes, have a factor in the bottom that's not in the top. X-intercepts have a factor in the top that's not in the bottom. Those are the three different ways that it could shake down. Here we go. Ready? Yeah, ready. So let's identify all the x-intercepts. What's this one on your graph? This is a root at -4. This root, call it root 2, looks like it's at 1. I know, because I saw the answer key, that this root is at -1. Okay? This root is at -2. This root is at -1. And this root is at +2. In case you couldn't see that, if I zoom in on this, you see how it dips below and comes back? It has two roots there. One at -2 and one at -1. So the first thing you could do in all these problems is you could make the numerator for all three. Let's do it. All right, let's make an equation. We know it's going to have a fraction because we're studying rational functions. That's what they look like. You kind of need a lot of room for the third one because it has 3 roots or 3 x-intercepts. So in the numerator in A, if the x-intercept's at -4, guess what? You're going to have an x plus 4. Two ways to think of that. It's x minus -4, which is x plus 4. Or we've learned throughout the year that left 4 is plus 4, right? Okay. The next root is right 1, x minus 1. I'm not done with this problem, but I'm going to move to B and stick with the theme of x-intercepts in red. All right, the next one has a root at -1, so what's up here? X plus 1. And how many does C have? 3. By the way, somebody thought it hit over here. It just goes forever like this, meaning it has what kind of asymptote? Horizontal. That means it's going to be bottom heavy. Remember that? Bottom heavy. All right, in C, tell me what the whole top's going to look like. X plus 2, that takes care of this. X plus 1, that takes care of that. X minus 2, that takes care of that. Are you good with the x-intercepts? Those are factors that are in the numerator, but nothing to cancel them in the denominator. If we're good with those, I'm going to go ahead and erase this just so we can get rid of some of the clutter. All right? What other features do these 3 graphs have? Good. Vertical asymptotes. I'm going to do them in blue. In the first one, I want you to draw a dotted line at -2 and 0. Just kind of darken the y-axis. In the next one, there's one at -4 and another one at +2. And in the third one, there's no vertical, just kidding. There's a vertical asymptote at 1. Okay? There's a vertical asymptote at 1. It also has a special kind of asymptote known as a slant asymptote. You see how it kind of tilts this way and goes like this forever? It's slanted. Slanted. That one is really tricky. It actually has an asymptote that's a parabola. If you want to figure out what its asymptote is, I'll give you a bonus. Don't just sit here and work on that now. Let's go back to A and tell me what the bottom is going to look like if it has two vertical asymptotes, one at -2 and one at 0. X plus 2 because of the -2, and x minus 0. You want me to write x minus 0? Or just x? Okay. I will, but you can just write x if you want. All right? The next one, we're just building these equations. X plus 4 because of the -4, and x minus 2. You see how we don't have exact matches in top and bottom, and nothing is canceling? If something did cancel, what would we have? A hole in the graph. Last one, vertical asymptote at 1. So what's down here? X minus 1. If they cancel, you have a hole in the graph. Yes. All right, now we're going to go back to the beginning. We have 9a. And the other thing I want you to make sure that the horizontal asymptotes are correct. In A, the horizontal asymptote is at 1. Is that normal when you imagine this foiled? What would this produce? X squared. What would this make? X squared. What's their ratio? 1 to 1. It's balanced, and the asymptote should be at 1. Is it? Yes. So I think we're good. I don't think we need a dilation in this problem. If the asymptote was up at 4, I would put a 4 out there. If this graph went all the way up here to like 5 and went across, I'd put a 5 out there. But it's not. It's at 1, so it's normal. So let's go to the y equals and go ahead and graph. When you put these in, you want to make sure that you use double parentheses on top and bottom. 1 to say, I'm starting the numerator. 1 to say, I'm starting the x plus 4. Then create the x minus 1. Then don't forget to close up the numerator before you hit divide. Very important that you do those double parentheses. Double open, x plus 2 times x double close. When we graph, we should see the graph of A. There it is. There's that mini parabola, and there's the other side. Everything looks normal. You might want to check a few things, like make sure that when you trace to 1, there's an x-intercept. And at -4, there's an intercept. At 0, there should be an asymptote, right? So there should be y equals nothing. And the bottom of this little parabola part looks like it's at -1, 6. Let's check that. There it is. So everything looks good. We can move on. Go ahead and put the next graph in y equals. So here's the graph of B. It looks right. And as we're looking at it, what do you notice here? A triple root. Did we have to worry about putting a cube to do that? Only with polynomials. These are rational functions. They kind of act differently. There's no need to put that little cube there. Take a look at the graph. Again, my batteries are dying. So yours is good. It's good. All right. Sometimes when people graph these, just so you know, when you look at your graph, it might look a little bit weird. Some of these graph them like this, and they quickly jump up and then do this, and then quickly jump up and do that. It's okay. Your calculator's just being a little stubborn, and it's drawing it kind of sloppily, right? But it's still okay. It's kind of showing you the asymptotes. The newer versions graph with a little more, a little better resolution. And here's C. We put the equation in. Notice the use of double parentheses there. When you graph, you might be fooled into thinking you're right. There's this kind of distorted parabola on the left and that weird line to the right. It looks pretty good, doesn't it? It's got this part. It's got that part. It's got this part. It's got that part, right? However, where's the y-intercept that we want? No, let's do this. Where's it cross? 2. The y-intercept of the graph that they want us to make is at 2. Where's the y-intercept here when we hit trace? 4. So it's too tall. How do we shrink it down? 0.5. It's twice as tall as we want it to be. All right? The y-intercept is at 4. We want it at 2. So how do we cut it in half? Put a little 0.5 there. One that doesn't disappear. 0.5. Try it. Go to your calculator if you already typed it in. Go to y equals. Second delete will allow you to insert. Second delete. We'll insert a 0.5 and graph. It makes it a little wider. It dilates it. Now when you hit trace, it's properly at 0, comma